Hello, everybody. Thank you all for joining. This is our Owens Design first webinar. So it's some of you have been at our facility for our technical seminars over the years, but this is a new venue for us. One of our customers, it's actually we've been working with SVXR for many years now, and I was really impressed about SVXR, where you're going to hear from Michael here. I was impressed with their incredible technology. It's not just about the sophistication of their electromechanical and X-ray, but also about, in particular, about their application software, which is really the reason I wanted to have this webinar and have Michael speak. A little bit about Michael. Michael Jupina has a PhD from the University of Southern California and the MBA from Santa Clara University. Michael is the VP of Engineering for SVXR and has been overseeing the SVXR high-resolution, high-speed X-ray imaging system for 3D and 2.5 IC packaging. And he has been more than 20 years experienced in the high-tech industries. Michael's expertise ranges from semiconductor to silicon failure analysis and X-ray imaging. Prior to SVXR, Mike was a general manager of Checkpoint Technologies, and there he actually expanded the company product line and developed 6 new products. And with no further ado, I would like to have Michael pick up the ball from here and talk a little bit about what he's doing and actually talk about this amazing technology that they developed at SVXR. And just as rules of engagement here, because since we don't want to interrupt during the presentation, you guys feel free to send questions live, and I'll capture those questions. At the end of the presentation, there will be ample time to answer those questions. So I will capture the questions, and at the end of the presentation, Michael will answer those questions. Anyway, thank you, Michael. Take it away.
Thanks, Toli. I think I'm now sharing my screen. So we'll go through this. First time for me also on this type of forum where we're going through a webinar. Just wanted to thank Otoli and the Owens staff for giving me this opportunity to talk to you. As you know, we were scheduled to do this back in March when everything got shut down. We're now doing this in a much more, I guess, proactive forum where we're able to show everybody what we're doing and still stay socially distanced. So thank you. When I first met the Owens staff a little over 3 years ago, we were a startup company with a very interesting idea and a lot of proof of concepts that came about that were really good, but we needed to put into a production format and hardware, develop the system and move forward. And that's where Owens became our key partner, and they were able to help us build this system, deliver it, and make it production worthy for fabs in Asia. So moving on. One more. Okay, so just a quick outline. We'll have an introduction and motivation about why we want to do inline and defect inspection for 2.5 and 3D integrations for packaging. We'll talk a little bit about the high resolution automated X-ray inspection system we developed and are now selling. Look at some cases, look at key elements of the system, and then go through a conclusion. So for us that have been working here a little while, you start realizing that the packaging has become very, very key to new products in the semiconductor field, where if you're looking at high-end processing where CPUs, GPUs, the packaging that's now required has tens of thousands of solder joints in them, and they're all very tightly bunched, and you've got to be able to monitor each and every single one of them. And the high bandwidth memory, we have similar issues where we're looking at data management, stack, die. How do we see solder joints? How do you inspect them, know that they're good? These are all very important things. So the markets that we look at are everything from mobile devices, automobiles, memory, etc. All very extraordinarily highly demanding products that need quality throughout. As we move from the 2D packaging, where we've had wire bonds and just some surface mount technology, the new technologies that we're putting together with the high integration, with the small form factor, lightweight technologies, is requiring to have high density solder joints, where we're looking at integrations of very small solder joints, up down to tens of microns, maybe even less on some of the products. So it's important to look at each one of these solder joints as we make them. The tens of thousands of connections in the wire bonds would have been impossible. So now we move into the 2.5, 3D integrations with millions of connections. And it's very important to then look at and monitor every single one of those inside a package. So just to take a look at why we're looking for zero defects, why we're looking at reducing defects to where they're going. If the complexity of a typical car that we're looking at, and we've got information here from both Audi and BMW about what it would take to have just a single defective device and what kind of cost it would come down to in terms of dollars and yield on the car is, it's just very important. So we need to look at, if you've got these different failure rates of 1 ppm at 4,000 cars a day, you're looking at 24 cars. So that's an amazing statistic. So we have to, the automobiles, look at self-driving, they need to have no defects, and they need to be able to move forward in a way that's very important to keep in track of all the solder joints and give us a very high quality, reliable device. So some of the things that are important is looking at the extended reliability of these cars, of the parts. In the cars, you're looking at things where the German automobile manufacturers are looking at years of life with zero defects. That's beyond comprehension for some of the packaging technologies in the past. The new smartphones are even looking at minimum 4-year lifetime. So it's very important that these chips last. And doing the solder joint inspection on a single joint level is imperative to get to these levels. The other thing that's very important is the SPC methodology that we've used in the past will not get you the zero defects, because it doesn't really look at the individual solder joints closely enough, and you need to be looking at a very small area, and the statistics in SPC just don't lend themselves to the part per million and less defects that we are shooting for. So this requires 100% inline inspection. This is where SVXR and its product, the X200, are aiming at and succeeding at in fabs inside factories in Asia as we speak. Yeah, one of the most important things on this is always fun picture. We've got our little zombie here walking around, and it's a walking wounded. The point is, even though you can go through all the AOI, SPC, electrical test, a solder joint like this would actually and could actually have passed all the inspections that are currently in place inside a modern day 2.5 3D fab. And so the point is, this gets out there, it passes everything, and if it gets into your cell phone, into your car, into your home electronics, it will most likely not make a lifetime that the supplier wants. And now we've got a very expensive package where we have HBM, processors, etc., that are failing due to bad solder joints. So what are the walking wounded type of defects? Well, let's just take a look at a variety of what solder joints look like. This top line is basically, these are parallel lapped cross sections of failed solder joints or one good solder joint. And what do we find with this? If we have a good solder joint, electrical test says yes, it works, and it can be found. Optical inspection can't even tell because it's buried inside the very complicated packaging. The voids here, intermittents, you can't see it in electrical test. You can't see it in optical inspection. Head and pillows, this is essentially a one form of not wetting, is, again, you can't see it necessarily in electrical test because it may be partially wetted on the backside, and its optical inspection buries it. So if you go through most of these, what X-ray inspection is needed for is to find these on a per pin basis in a very complicated package. The other ones, the non-contact open, obviously we're not making contact, and the bridge short where two solder joints actually are shorted out between each other. So again, these could be found in electrical test. It all depends on what are their device, their function of the pins are. So what is missing? Well, we need to have a methodology that the SVXR 200 X200 customers will get with the first inline X-ray inspection system. It's non-destructive, it's fast, it's transmissive, so we can see into the devices where we can look at the multitude of solder joints. High resolution where we can actually see down to micron level defects. It's very important that we can see that. And we have an automated system that allows us to automatically load wafers, substrates, whatever the parts are presented to us on. We've got a very flexible system, and we can look at tens of thousands of solder joints in a given part and look at every single one of them. So this is basically a high resolution automatic X-ray inspection system. That is the SVXR X200. Here you can see that system as it sits on Owens manufacturing floor. It's designed for inline inspection. It's 100 times faster than the standard systems that are out there. The standard systems that are out there are essentially failure analysis review type tools. They have a very complicated system that allows you to look at individual solder joints, but not the entire device. So that's the fast portion of it. The AI-based, we have developed image processing as well as artificial intelligence-based methodologies to look at the individual solder joints and then inspect 100% of the solder joints that we see in a device. The other thing that's very important is it's non-destructive. Some of the ICs are extraordinarily sensitive to X-ray and they could be damaged, but we have a hardware and methodology that allows us to make the X-rays for imaging in our system not damaging, even to HBM and DRAM memory cells. So it's very important that we are non-destructive and do not affect the long-term reliability of the devices with our X-ray inspection. Also, just to point out, this is a very flexible system. It has a capability of 300 millimeter wafers down to film frames, strips, carriers, whatever that is. We can use that and look at our customers' devices in almost any format. The point of the system, again, is getting our customers up to yield quickly, being able to look at multitudes of solder joints is the most important thing that we're providing here, and it allows us to have a very fast yield ramp where we can dial it in and actually get to a higher quality going out of the factory in a faster method and a faster way of doing that. The points are we can look at in NPI bringing products in, we can identify the product issues there. We can then determine them faster because we are sitting literally in the production line, and we can give feedback to the process steps that are soldering and creating the product in a much more faster and effective manner, and will allow us to feed the information back to it and look for root cause and come up with better MPI, high volume manufacturing capabilities. So another thing that's very important, as I mentioned just briefly earlier, is we have a inline inspection. It's a new technology that I'll explain a little bit later on in terms of hardware, but the typical review 3D CT does not have a large field of view. But if you know where to look, it can help you see very nice and very important features in there. So what we have done is we've come up with imaging technologies inside that are able to inspect, identify potential problems, and actually classify them in some cases, and then send them off to the review tool to get confirmation of that. And we feed that back into our AI and get continuous improvement on our models. It's very important that we have the defects identified and labeled and sent back, because in reality, the processes that our customers are using are quite high yield, but that means we don't get a lot of identified defects that are labeled a priori. We find that out after we identify them and go through some sort of review process. So we need to have both the high resolution automated X-ray inspection as well as 3D CT. They go hand in hand. Some of the different insertion points for our system, and we've in fact have got to almost all of these in our first introduction product. We're working right now at looking at the memory stack with the very small micro bumps with 10 to 40 microns, and then the bumps that are around 80 microns and going up. There are essentially different insertion points that we can look at. It's very important to try to get the inspection done as close to the insertion to the process point that could cause the defects. Okay, so let's talk about some implementations of our technology. As you can see here, this is a typical output from our system on top, just to graphically represent to an operator, an engineer, what is going on. This is a 2.5D package that one of our high volume manufacturers. We are supplied with a Gerber file that tells us where the solder joints are. We then look for defects within each of these solder joints. This image on the bottom left is an actual image from our top-down single view X-ray source. And what we see here is we've got a multitude of bridges. And that is then identified in our second image here, where you see the extra solder being in red and the missing solder being in green. So we can identify how solder heads moved. And then over here, this is actually our inspection area where we identified and located all the appropriate pins that we are inspecting. This allows us to come up with nice artificial intelligence models that will look at the different pins, judge them, and score them, and call them out to the manufacturer, our customer. This is one of the more interesting examples that we've had, where we've had a system in package. This is for a cell phone implementation where the single IC that we're looking at here, we don't really outline it completely, but has tens of pins in it, and what we are seeing is non-wetted pins on one side and wetted pins on another, and then partial in the middle. What that tells us is there's definitely a problem with this, and where it was not necessarily detected by electrical test. But when you do the ECT, you can see that we're squishing solder out the side. It pulls this side of the die down. That's this line here, and the green one is this line of joints there. It pulls this up, so these guys are barely making contact. So this is a way that we can do this, and this was done in an automated fashion. This is on the factory floor, and as it ran through, we were able to use the image processing that we have and artificial intelligence to judge these solder joints of what was potentially non-wet. And we know by the functionality here what the part was bad, and we can call it out automatically and put it into their factory host as it through SexGen interface. So another methodology we have is just looking at how do we see the solder from the top, and a lot of what we're looking for is solder shape and sizes that are varying within the ICs that are being packaged. Here you can see where we have the extra solder is red, where it's squishing on the side, and we're missing it on this side. This is for us to go back and find a good way of metrology, feedback into the solder process development, and make a very fast and reaffirming method to close the loop and cause the quality to go up and fix problems before they actually leave the factory or even get to a test point. If you take a look at this is then just what happens when we're seeing going across here. It's similar to the slide previous, where we're missing solder, pulls up on the die, and here on the end where we're squishing solder out, it pulls it down. So this is what is happening physically, but all we are getting is an X-ray image that looks around here that our image processing and AI are using to then allow us to judge this IC as being soldered improperly and call it out as a reject in the factory. One of the more interesting process monitoring AI task that we took on here was one of our customers supplied to us 3 lots to us in a blind sample, where they gave us the process of record, which is lot B. We have a lot A, which they told us later was a variation on how long the part sat after being placed on the substrate, and then the lot C was the temperature in the reflow oven was slightly above where it was nominally. What we used was a artificial intelligence AI modeling technique that looked at all of these. We imaged about 5,000 parts with this and trained our machine to take a look at it, and then we were able to come back with what lot it belonged to. So we were able to very accurately predict the lot A added time was in this sector of the graph, the temperature here, and the POR was there. This can allow our customers to now monitor their process so they can see when it starts to move away from the nominal process and catch process variations and drifts before they affect yield in the product itself. Our accuracy on this was over 95%. Okay, so let's talk a little bit about our system and how it works. We have essentially three parts that are very critical to us. And when I ever talk to our customers or anybody who comes in wants to know what is the importance or what are the key elements of SVXR, it starts off first with our imaging technique. And I'll describe that to you in a couple of slides. But our imaging technique is unique because it allows us to look at large fields of view, get high resolution, and go at a speed that matches the line speed for assembly. That's like the key basic element of the hardware. The analytics and software that we run is the next most important thing, or the most important thing that the customer sees is we're then able to go run the machine at the appropriate speed and do the analytics in line. So as the part comes out, we have a judgment on the part. It's very important that we can do that. It has a large data array. We've come up with our features that we have to generate, and then we look at the analysis of going through image processing, artificial intelligence. Lastly, there's a visualization portion of it. And how do we see what's going on inside there? Because sometimes it's not so much a scores that we can say that's just numbers, and our AI engineers love the numbers, but to get down to somebody who's actually worked on the factory floor, you need to be able to see what's going on. So we have to come up with an effective visualization technique. And we'll show you a little bit of all that here moving forward. So the traditional X-ray systems are essentially what is called a point projection system. It relies on the size of the spot in the X-ray source for resolution. And additionally to that, it relies on the distance from source to object and then source to detector for magnification. So the magnification is just the ratio of the long distance divided by the short distance. So that is necessarily meaning we are very, very close to the X-ray source. It is also, because it's a small spot, you cannot have a very high power source. Those limitations basically allow you to do some very nice things in 3D CT. You can tilt, you can move all sorts of things around, but it also slows you down. So a typical 3D CT would take hours, where we would take seconds. The other limitations that are necessarily understood is the detector, in terms of size, is relatively large pixels, even though we get a large magnification on that. But it's only the state of art may be about 10 megapixels, but the typical systems are under 10 megapixels. For the SVXR, we've eliminated the source size as the resolution limitation. We have a 1,000-watt source, much higher power coming out. We have a longer distance from the source that allows us to illuminate a larger area of the device with the same sort of resolution on it. We have proprietary optics and detector that gives you 30 megapixels. And one of the more important things we need to bring out, I'll show you in the next slide, is it's a excuse me, a 16-bit bit depth on the camera that we are using. Having the 16-bit data depth allows us to come up with pseudo Z and thickness measurements of the solder, and we'll talk about that. So the other issue that we also have is not shown here explicitly is how we condition the source spectra to remove damaging X-ray energies. There's studies that have been done on which energies are damaging the oxides within ICs. We've identified those and we're able to filter those out while still allowing the imaging photons, if you will, to go through the device and give us the appropriate images that we need to see. And it doesn't affect the throughput on the machinery. So just for an example here of why the high dynamic range is important. This is a typical X-ray. We've got 16 bits of data here. But as you can see with human eye, projection screens and everything else, basically what we're seeing is a kind of a gray area, a bright area, a dark area, and some sort of transition. That's great because we can then plot that out, take a look at it, and we can see what the slopes and what the additional gray levels that we are getting out of our high bit depth. What that then tells us what is happening within the solder joint. You can't necessarily see it here in the dark area, but we are seeing that there's definitely a slope here that we don't necessarily see. How does that come about? It's essentially, if you take a look at a contact non-wet, the good joint is hopefully just a cylinder coming straight down, and the X-ray image becomes sort of a flat top, a nice square wave like this. But when you start looking at the non-wets and the non-contact, the edges are rounding, which then give us a slope on the profile, which we can then identify. And we're identifying these through features in image processing, as well as some other methodology we use in AI that we are using to feed into our models. The analysis software that's very important here is, if you take a look at this, is we're looking at a series of parts that we are at image, and we are able to look at individual dies as we come through. These are all good, 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 and we're giving our scores next to the pin, and then you can see that one is bad. It allows us to look for, our analysis is then demonstrated and shown to the customers in a manner that allows them to see exactly which die, which pin are defective within a given analysis that we have. It's very important that we take a look at everything down to a pin level, because there are very important ensemble measurements that need to be made for the entire IC that's being soldered down. So this allows us to then judge every solder joint, then an individual IC within a package, and then report that package back to the factory host via SVXR, so that the customers can then pull them out of production and then also have all the information they need to go back and do the appropriate failure analysis on the parts themselves. Okay. So what are some of the challenges? Well, it's interesting because my original, or one of the careers I started off with, or parts of my career, was working in the wafer fab, and I was very impressed at how accurately items could be processed on a wafer, and they're down to now being sub-nanometer positioning, right? But inside a package, that's not happening necessarily. There are metal plated core vias that and trace pads, as well as other metallic devices in a package that create X-ray shadows. That's essentially what an X-ray image is. It's a shadow-gram of what's in the part. So the most important shadows that are being created for us are the solder joints themselves. So these vias and traces, etc., with respect to an IC, move around a lot, which means they move around tens of microns. So there's inside the part or package variation. Then we have other parts where it just moves the IC itself a little bit. So there's these part-to-part, substrate-to-substrate variations that we need to take a look at, as well as then we have to come back with validation. So the validation is some of the most important parts. I mentioned earlier, the current DPPM that where customers are going at are in the hundreds of DPPM, and they're pushing down into tens and maybe even single digits moving forward. So you don't get a lot of actual labeled bad solder joints from the beginning. You have to go back and validate it. And what that means, you got to go back to a 3D CT, go get parallel lapping and validate them, and then feed those labels back in. It's a very important part of the process. The other thing that has become very interesting to me and to our team here is the there have been several efforts on our part with our customers to come up with program defects, if you will. Vary the process so that we can get more defect count within a part. But every time we seem to do that, yes, we get more defective parts, but it also changes the fundamentals of what we are looking at. It's very hard to create a defect without affecting the whole part, and then what is normal in one part becomes normal throughout the whole process. So we got to be very careful on how we do that. So the validation and feedback into the model is one of the most critical steps that we can have. Okay, the typical application development cycle that we have is we need to look at what are the pain points for our customer. That's the most important thing actually is where are our customers needing our technology. We need to get some good samples from them and as well as some bad samples. That helps because when we have that comparator, we can image them very quickly, and then we'll take a few weeks to go through them and understand with our application scientists, our algo scientists, and the imaging scientists of what are we looking at. We're getting a pretty good idea of how these things work moving forward, but it's important that we have that step where we're very well engaged with our customers, what their pain points are and what are the known good and bad samples. The analysis cycles that we go through is looking at what are strictly outliers. And that's important because if we look at the outliers, then we can take them off to a review tool that allows us to get a very detailed look at a given solder joint and then confirm or not deny, but come up with this is actually a good solder joint, but it doesn't look normal, which happens quite a bit. It allows us to come up with improved feature generation, outlier detection, and feed that back into our models. During the industrialization phase, we do things that are very important for our customer in the end game of it, which is being able to breed in EMAP, be able to feed the information back out into the factory host so we can see very accurately which die and solder joints are failing. We've worked on methodologies of automated handling, as I mentioned earlier. We have EFEM options that are allows for wafers and film frames to be loaded into our system directly and be controlled via SexGem. We also have methods that will allow us to bring in strip material that'll come through. We have data reporting that allows us to, again, look at the lot, the modules down to the individual pins, and we're able to help and feed back to the system very quickly. So as the conclusion, as we get to the point where we have more and more complexity, you're going to need to have more and more inspection, and that inspection is going to have to be high resolution X-ray inspection that's in line at speed. So we've been able to look at multiple methods that allow us to have the inspection, metrology, and process monitoring to move forward into the modern day packaging factory. Thank you very much. Hopefully there's some questions coming forward to me.
Well, thank you, Michael. Quite impressive technology. So I do, thank you, everybody. I will unmute you right now, and feel free to either send it via chat or just ask the question and see if we can answer that. So there you go. Should have, let's see. Yeah, so you need to unmute yourself. I actually unmuted you, but if you want to ask a question, you will need to unmute yourself and ask Michael a question. So, and while here we go, Alex, go ahead.
Hey, Michael, question to you. Is this system supposed to support manufacturing line or more of failure analysis lab?
This is for manufacturing line specifically. That's what our design was from the beginning. So we're not trying to be in the failure analysis lab. So it has been deployed now several times into a manufacturing line in Asia.
And what kind of throughput or cycle times, can you talk about
that? Sure. What we are getting is an inspection rate, and being the engineer, the easiest way of talking about it is the 3,000 square millimeters per minute, which basically, depending on how much area of a wafer you need to scan, is a few wafers an hour. We've gone through some of the larger CPU, GPU, 2.5D methodologies where we're able to look at over 100 units an hour. And then if we look at the cell phone parts that are much smaller, we're able to look at 5,000 units an hour. So that's, it's a lot of information, but it's, it is able to go quite fast.
Thank you. Appreciate the answer.
No problem.
Anybody else? Any other questions? By the way, feel free to email me further questions that you didn't have a chance to ask today, and make sure Michael will get those questions and answer to you. Anybody else? Well, I think I don't see anybody else, so I guess this is it for today. I really appreciate Michael. This is I learn actually myself a lot. I've been working together for so many years, and finally I get to understand a little bit what I was working on. So it's just educational for myself and for the team. And appreciate your time and sharing with everybody your knowledge. And yeah, thank you everybody for joining, and hope to see you to our next webinar. Take care. Take care, everybody.
Thanks.
Thanks, Michael. Bye.